Hi, everyone. We'll start lecture 9. And this is just going to be a continuation of what we started last time. So we talked about linearity and superposition as a consequence of linearity. And then we started the discussion on equivalent circuits and the general concept of equivalence. And I made a very brief introduction to the Thévenin and Norton equivalent circuits. So what I'd like to do is to just take it from there, start with the Thévenin and Norton equivalents, and define them relatively broadly and generally, and look at what they mean and how to go about using them. Okay. So I'll start maybe with a more or less formal definition. Thevenin equivalent circuit. So there is a theorem that says if you have a linear circuit, now recall what a linear circuit was, a circuit that comprises linear elements, linear relationships. And so in this particular case, we are limiting the discussion to resistors, sources, independent sources, voltage and current, as well as dependent sources that again have linear relationships. So if you have such a circuit and you take any 2 points somewhere in the circuit and look at what happens between those 2 points from the outside. So you attach some wire to it, you put the rest of the circuit in a box, and you just have these wires as points of access. And you look from the outside. That circuit, you can replace it with an equivalent circuit as far as the outside world is concerned. And that equivalent circuit simply includes a voltage source, an independent voltage source, in series with a resistor. Okay. Now, if you think about it, that's a very powerful statement. So let me write it down, and we'll try to get some insight into it. But so Thevenin's theorem. If we have a circuit comprising resistors, and we mean ohmic resistors, so linear resistors that or resistors that are purely linear. They have purely a linear relationship. They follow Ohm's law. Comprising resistors, independent sources, and dependent sources that have, again, only linear relationships. So if we have this, and then if we look between any 2 points. Now, when I say any 2 points, maybe we should be a little careful about that. So I'll put an asterisk here. So that we remember to come back to this. Any 2 points in the circuit. From the outside world. The behavior of the circuit can be represented by that of an independent source and a resistor in series. Sorry. Between those 2 points. And by points, I mean nodes, two places where you can connect, let's say, a voltmeter or something else. So this is what we mean by this statement. Take a circuit that has a bunch of things in it, and it's inside a box. So you have a bunch of resistors, a bunch of independent sources, and a bunch of linear dependent sources. And there's many of these, and they are connected in a very general network. And out of this box, you bring 2 wires that are connected to 2 points in that circuit. Well, the theorem is saying this is equivalent from the outside world to something like this. That just has one voltage source. So it's this. And one resistor. Now let's see if we can feel that. You can prove this, but let's see if we can feel what's happening here. So when I say the behavior of the circuit from the outside world, it means I'm doing something here, right? So I'm connecting this to something else. Let's say I'm connecting it to another resistor, another circuit, a voltage source, maybe applying a voltage, measuring a current, all sorts of experiments. So I'm building basically a bigger circuit that includes this box as part of it. Or I should be talking about this really still. That a bigger circuit that includes this as part of it. And I'm saying if I'm interested in what's happening outside the box, I can replace what's happening inside the box with this. Can anyone think of an argument, a little bit of insight, intuition as to why this should work? Why is it that we expect something like this to work? It's a big statement if you think about it. I'm saying you can take a circuit that has 1 million elements in it, and from the outside, its behavior will look like this. So that's a pretty big claim. But intuitively, why should this be expected? Or how can we come to terms with it? Yeah. So that's one very good insight. You're saying, well, a resistor takes care of the slope of a curve. If you're thinking about a curve or a graph, voltage versus current, an IV characteristic, with one resistor you can represent any slope. And with one source you can shift that line with whatever slope. You can shift it up and down wherever you want. So that's a very good insight. So you're saying this small box, or this box with just these 2 elements, can do a lot. So that's one thing. You wanted to say something else? Yeah. So that's the other piece of the puzzle. We just already argued that one voltage source and one resistor can give you any straight line with a slope, a fixed slope, and shifted vertically. And then the other piece of the argument is, well, we have to argue that this big box, the original box with all these elements, in fact, we expect it to be something that ends up with just a straight line with some slope shifted somewhere, right? And that's really based on the linearity property of the whole circuit. Recall that we said if you had a big circuit and it had only linear elements, and given that you have KVL and KCL relationships which lead to linear equations, any voltage or current in the circuit would end up being basically a linear combination of all the voltage sources and current sources, right? We had a statement like that in your notes from last time. As I said, if you have a big circuit, you measure the voltage anywhere or the current anywhere, you will see that it will be a linear, you can represent it as a linear combination of all the sources. So something like this. I think we wrote something like this last time. V sub j being A1j source 1 plus A2j source 2, and so on. Sorry, I should say nj source n. So if you have n independent sources, any voltage or current in the circuit would be a linear combination of those. And in fact, now taking this and thinking that if you're building a bigger circuit around this, so looking at this from the outside world, that in this bigger circuit, also this relationship will hold, then you will see that this linearity property will lead to the fact that what you see for that box from the outside will also be represented by a straight line, albeit with some shift that for which you need this voltage source. So this is really the root of it. Again, I'm not going to write in detail as a matter of rigorous proof, but I just want to invoke maybe that intuition or insight that it really comes from the linearity. And no matter how big the circuit is, between a given set of 2 points, it will behave in a manner associated with the, maybe you might say, the smallest linear circuit. So now if we have extra time at some point, or if some of you guys are interested, we can try to do it a little more rigorously and do it as a matter of a mini proof. But for now, I think it's something that maybe it would be more useful to see in practice and develop some intuition for it. Okay. But this is what the theorem is. And in fact, it's more common to, you'll see it mostly drawn like this, a Thevenin equivalent circuit. It's more common maybe to see it on the left-hand side, like this. It's exactly the same thing. I'll just put it like this. And this resistance would be called R Thevenin, and this voltage would be called V Thevenin. And you would put it in a box. Now, the important thing from an application point of view is to, maybe the first thing is to draw the IV characteristics for this circuit. So let's do a mini exercise here together. So if I do this, and I ask you to give me the IV graph here. Could you try that on your own? So I is that current. I've defined it that way. V is that. Who has the answer? OK, so let's take a look. First of all, if you're troubled by the fact that I've shown this with this node open here, and I'm asking for V versus I. So you might be saying, well, there's nowhere for the current to go. When I say something like this, and all I'm asking is to say what V would be if I were some value, and do that as a function of I, right? Which really means if I were thinking of an experiment, that I would be something like this. Let's say putting a current source here and then measuring the voltage. Or maybe easier to think of putting a voltage source here and measuring the current. So this is a voltage source, let's say V, and that's an ammeter, so it's measuring the current. So I apply a voltage and I measure the current. And so you can do this for a few different data points. So if I apply, let's say 0 volts there, what will that current be? Well, you have one simple KVL. So this is 0 volts. How much is the voltage drop across the ammeter? An ideal ammeter, 0 volts. It does not influence the circuit in any way. So 0 volts, a simple KVL will give me the value of the current. So if V is 0, I will be V Thevenin divided by R Thevenin. Let's say this. And let's find another data point. So what value of V would we need to get a current of 0? Let's say if we want to be on this axis. So if I were to be 0, it would mean I should have no voltage drop across the resistor. And given that the ammeter has no voltage drop, I would need the two voltages there to be the same. So V Thevenin is in fact the point where this crosses the vertical axis. And this is a linear relationship. You can try this for other points. You can try it for any value of I and calculate V, and you will see that you will fall somewhere on this line. Or conversely, put any V and calculate I, and you will see that you will fall on this line. So this line has a slope of R, well, in this case negative R, because of the way the direction of the current is. And it crosses the vertical axis at V Thevenin and the horizontal axis at V Thevenin divided by R Thevenin. Incidentally, there's also a name for these points. That voltage corresponds to I equals 0, right? As you see on the axis. I equals 0 meaning there is no current going through, is the situation where you don't have any connection, right? If the circuit was completely open and you just put a voltmeter there would be no current. You would measure that V Thevenin. Because current is 0, this is called the open source voltage. Open circuit. So a general name for this would be VOC. Conversely, at this value of I, there is no voltage drop there. So that's the current that you would get if you put 0 volts here, which corresponds to a short circuit here. So that value is also called a short circuit current. This is a good terminology to be familiar with, because you will see these expressions used broadly. For instance, if you look at photo cells, photovoltaic cells, solar cells, you will see this kind of terminology. So in electronic devices in general, you will see a lot of usage of open circuit voltage or short circuit current. Okay. So our open circuit voltage is simply this V Thevenin, and our short circuit current is V Thevenin by R Thevenin. So question then, if I give you a circuit in a box with 2 wires sticking out of it, and I say, I promise everything in this is linear, and it follows Thevenin's theorem, measure for me the value of VTH and RTH. What would you do? Yeah, exactly. You do basically these 2 experiments. One is you measure the open circuit voltage. What does that mean? It means leave the circuit open at those points. Measure the voltage that appears there. Now, when you connect a voltmeter somewhere, you have still left it open, right? Because a voltmeter does not draw any current. An ideal voltmeter, of course, is approximate. But it just tells you what the voltage there is without drawing any current, without imposing any load. So a voltmeter connected there will just give you the open circuit voltage. And you know immediately that that's your Thevenin voltage. How would you do it on paper? Well, you would just leave the circuit alone. So or it doesn't have to be this. So this is actually our general circuit. You have 2 wires sticking out, and you have many elements in here. You just measure, quote unquote, on paper, in this case, the open circuit voltage, which means you just calculate the voltage between those 2 points. So calculate or measure using a voltmeter in the lab. This voltage V. That is your open circuit voltage. Which for a Thevenin equivalent just happens to be VTH. The Thevenin equivalent voltage will simply be the same as that V open circuit. So that's one thing to do. The next thing you want to do is to calculate the short circuit current or measure. So step 2 would be, again, you have the same circuit with a bunch of things inside. No, sorry. Yeah, so that's V. But in this case, I'm interested in the short circuit current. Now, how do I measure the short circuit current? I connect an ammeter. And an ammeter, again, has 0 volt drop across it. So it really is like a wire, an ideal ammeter. It's just the wire that has a number on it that you can read. And that's the current going through it. Now, we are interested, notice the way I have defined the convention for the current there. If I want a graph like that, the current going from left to right. So this is the current that I'm interested in. So calculate or measure using an ammeter in the lab this current. That's your short circuit current. The Thevenin resistance will simply be, look at that, VTH or VOC divided by RTH is ISC. So the Thevenin equivalent resistance is simply VTH or VOC by ISC. So this is basically about how to find the Thevenin equivalent of a circuit. Two simple steps. Now, if you're trying to calculate this on paper, you don't need to show an ammeter, right, or a voltmeter. But you do need to make sure that you have connected a wire here. And notice that these two circuits, the two circuits shown in 1 and 2, are they the same or different? They are extremely different. They're entirely different, right? Oh, maybe I'm exaggerating just to make a point, but there is obviously a lot of similarities in that they include a huge chunk of the same thing, or they include the same thing as part of them. But sometimes adding one wire between 2 points in a circuit could make very, very drastic changes in its behavior. The whole thing is changing, basically. Because remember, again, when you're solving a circuit, you are dealing with a series of coupled equations, right? If you have a system of 1 million equations and 1 million unknowns, and if you change one of those equations, in principle, all the answers could change, right? So the two circuits are different, and if you solve them, you would, in general, get different answers for different things in the circuit. But they, of course, have a big chunk in common. In fact, the top circuit is embedded in the bottom one, right? Because the top circuit is really just, you're doing a reading, but the bottom one, you have actually added a wire. So that's a very crucial thing that I want to emphasize. When you actually do exercises with this, excuse me, what you should remember is that really this is two separate steps, two independent steps. They should both be done. And for each of them, you have to calculate the entire thing from scratch. Now, you might end up in some cases with an example where there are simplifications that lead to maybe small differences. But in general, you need to redo the whole thing. Okay? So to emphasize that here, a voltmeter, if you attach a voltmeter there, you're looking at an open circuit. If you attach an ammeter, you're looking at a short circuit. Okay. So on paper, you would literally add that wire and then calculate that current. Now, is there any other way? Are we absolutely required to find the Thevenin equivalent of a circuit to find the open circuit voltage and the short circuit current? Is there no other way? Okay, very good. So yes, there is. Yeah, so get any other points. So look, this is a straight line, and you just need 2 points to define it, right? So you don't need to measure the open circuit voltage and short circuit current. You could have measured other points. So imagine you have a voltmeter, a voltage source that you put there, and an ammeter, and you apply some voltage, some value, and measure the current. You get a point here. You apply some other voltage, get some other current. You get a point there. Straight line goes through that. And of course, from that, you can then, if you're interested, calculate your open circuit and open circuit voltage and short circuit current. So what I said here should not be treated as a, as too much of a rule set in stone, but as a guideline maybe, because perhaps is easier. This is a relatively easy point to calculate, right? You just calculate the voltage between 2 points. And here you just added a wire rather than adding another voltage source. But it was not absolutely necessary. So this is the Thevenin equivalent of a circuit. Now, how are we doing time-wise? So let's look at an example. So the same example that I drew last time. So find the Thevenin equivalent. So now when I say Thevenin equivalent, between which 2 points? So if I have put this in the box, and I say find the Thevenin equivalent, it's meaningless unless I specify where the wires are that come out of the box. And so in this case, I would say between points, let's say this and this. So equivalent between points A and B. Yes. Oh, sorry, I forgot to specify that. I think it was in the middle, but let me double check. Yeah, so this is I0 and this is V0. So when I say the Thevenin equivalent between those 2 points, what I really mean is it's as if I had basically attached the wire here, or let's bring it like this, and then another one here. And so this is just a wire, so point A and B, right? Now, I might not specify that in the future. I might just say between points A and B. But this is what is implied. So I have the whole thing in a box. And I'm asking for the Thevenin equivalent between points A and B. So maybe just give it a try for a couple of minutes. And again, I don't need a full solution. It's a big circuit. It might take a while. But just to see that those two steps make sense for you. Okay, so if you have had a chance to think about it, let's take a look together. So if I wanted to go by that same approach of looking at the open circuit voltage, well, that's basically the voltage difference between those 2 points without attaching anything between them. So we are keeping the circuit open outside. Now, by the way, when I say this may be important to emphasize, when I say open circuit, it doesn't mean that there is no connection between those two. There is, of course, all the connections of the original circuit between them. But from outside the box, I'm not adding any connection, right? So the wires outside the box are open. So this really boils down to just solving the circuit as is, and then finding the voltage difference between the 2 points A and B, which happens to be the voltage difference or the voltage drop on the resistor 10. So for step one, if you call this, let's call this V1, all you have to do is to solve the circuit to get V1. And your Thevenin is simply that V1. It's something you can do at home as a just practice problem. All you need for that is your KVLs, KCLs, element relationships. For step two, you need something additional, and that's why I'm using a different color. Instead of redrawing the circuit, for step two, I need to add a wire here, right? And I need to measure this current or calculate this current. Doesn't matter if I draw it up there or down here. That's that current. So for step two, solve this new circuit now with that wire added. With the green wire added. To get, let's call this I. I have nothing else there. To get I as indicated. And your short circuit current is simply that I. And then finally, our Thevenin is V Thevenin divided by that short circuit current. In the circuit, you will see immediately that when you add that wire, it essentially bypasses that 10 ohm resistor at the top, right? So it immediately makes the voltage drop across that resistor 0, which then could have really major consequences for the rest of the circuit. So it really has to be calculated again. Now, if we were to maybe add a little bit of fun to this example, if I said, find the Thevenin equivalent of this circuit using superposition, what would you do? Yeah. Exactly. So basically things, these are now methods and techniques that keep adding on. If you wanted to use superposition, that would make no difference in the approach to finding a Thevenin equivalent. But when you want to do step 1, let's say, to find VTH, you can use superposition, namely solve the circuit for one source at a time, like we discussed last time, and then sum the results up, including their signs, and then that would give you your VTH. And then for step 2, make this new circuit with this wire added, and then again solve it to find this I, the current through this wire, once with only the voltage source present, and once with one of the current sources present, and then with the other current source present. So superposition is just a method to solve the circuit, and all you need here is to solve the circuit. So you can, of course, use superposition too. Okay? So I think this is a good time for a break. So I'd like to introduce the Norton equivalent, but before doing that, there were a few questions here that I think maybe make me think we have to have a quick reminder of a few things. So first of all, note this important reminder that I put here. So I added this green wire connecting A and B in the second step. This was not there in the first step, right? In the first step, I just wanted to know what the difference, what the voltage was between point A and B. Okay? The open circuit voltage, meaning the points A and B outside the box are not connected. That just happened to be, in this particular example, it happened to be equal to the voltage across that 10 ohm resistor, which I've indicated as V1. Imagine my point B was somewhere else. So let's say if I had point C somewhere here. And if I said, give me the Thevenin equivalent between points A and C. Now, the open circuit voltage I'd be interested in would be the voltage difference between points A and C. Again, you would have to solve the circuit, the same circuit that you solved in step 1 before. But this time, the voltage of interest to you is the voltage between points A and C. So that includes the voltage drop, for instance, across this dependent source, dependent voltage source, 2I0, plus the voltage drop across this current source, one of those two current sources. And remember again that a current source could have any voltage that comes out of the solution of the circuit. So you have to have that voltage drop calculated. And then having those two voltage drops, you can calculate the voltage drop between A and C, making sure you take you pay a special attention to the directions, polarities. Okay? That would have been my VThevenin for the equivalent circuit between points A and C. And that would have been a very different Thevenin voltage. The Thevenin equivalent would have been different. And then to calculate the I-Thevenin for that, I would have to connect the wire between points A and C and solve that circuit, get the current going through that wire, which is again a different circuit. And that would have been my short circuit current. Yeah, so in that case, I would have brought the wire out. Same circuit, but from a different point. And it would give you, in principle, an entirely different Thevenin voltage and an entirely different Thevenin resistance. So the equivalent circuit, so this is really the key point to remember, that the equivalent circuit, equivalent Thevenin circuit of a circuit, so put it this way, if I say give me the equivalent, Thevenin equivalent of a circuit, that's not a complete question. I should say between which 2 points, okay? That's really critical. So a Thevenin equivalent is not the property of a circuit only, but a property of the circuit between 2 well-defined points. Okay? Which also then brings me to this this little star I put here, between any 2 points. So if you look at the way Thevenin's theorem is written, very often you will see it said between any 2 points that follow Kirchhoff's current law. Okay, I haven't put it that way. But this is what is really meant. If you look at this box, any of these examples that or schematics that I have, including this example, the entire circuit is contained in there, right? So if I brought out 2 wires from points A and B, imagine, again, forget about the green wire that I added later, but consider the 2 wires that I connected to points A and B, the blue wires. The entire circuit is in a box. There's no other connection to the outside world. So if there is any current in any circumstance, so let's say I have connected this to something else, a voltage source, another circuit, whatever, and now there is a current going in through wire A. Well, that same current should be coming out through wire B. Okay? Because if not, it means charge is being accumulated inside the circuit, right? So that's what is meant, that when we say between any 2 points, when we define the Thevenin equivalent, this is meaningful as long as we haven't connected these points to something else somewhere else. So that's one really important thing I wanted to emphasize, that when we say between any 2 points, you have to make sure that the rest of the circuit is contained in a box, not connecting it somewhere else. The other thing is, sometimes you will see people explicitly say, as long as those 2 points are not directly connected with a wire, or they're not directly connected with a voltage source, and so on. And those, I think, I prefer to think of those as special cases. For instance, let's just think as an example. If I had the same circuit, but for a moment I'll add something. Say if I had the same circuit, but something else inside, another voltage source here. Let's call this 2 volts. So imagine I have the original circuit plus this. What is the Thevenin equivalent now, looking between the points A and B? It's just that voltage source. It's a 2 volt. The Thevenin voltage is 2 volts. And the Thevenin resistance is zero. So think of it this way. This 2 volt, now imagine this is a power supply. So if I had drawn it like this, going back to how redrawing a circuit can make things look very different, right? So what if I had drawn it like this? I have a 2 volt supply here, and I had connected it like this. Okay? And then I also have connected it like this. So it's a 2 volt source connected once to this circuit, and once I have brought it out for some other usage. The same way you have the wall plug, someone connects a projector here, someone else connects something else somewhere else, right? The fact that you have a refrigerator connected maybe in the lounge to the wall doesn't really make a difference to what we see when we connect our laptop charger to the wall here, right? So it's the same. So be very careful with things like that. And again, I'd rather not list these as exceptions and special, exceptions and get too excited about them, but just point them out as some special cases that, so in that case, you just have a voltage source. R Thevenin is 0. And if you go to the characteristics, what happens? How will this line change? V Thevenin will be the 2 volts. If you just put a voltmeter there, you will just measure the 2 volts. This line will be flat. It will be, right? There will be no slope. R Thevenin, what does that mean for R Thevenin? So this point is going to infinity, basically, right? This line is going up. This point is shifting to infinity. Means R Thevenin has become 0. So V Thevenin over R Thevenin has become infinity, right? It's just a voltage source, 2 volts. So no matter what you connect to it from the outside, it will give you that flat 2 volts. Okay. So be careful with things like that. Here, and that's why I put this star here. So let me underline and maybe put a note here. Consider special cases. Okay. Yeah. So the question was this. Now imagine the other problem where I said, let's see what the Thevenin equivalent is between points A and C. So if I brought out a wire like this, I said that the Thevenin equivalent between points A and C rather than A and B. So scrap B, between A and C. And so you have, again, the open circuit voltage that you have to calculate, as we discussed. And then you also have to then calculate the short circuit current, right? And the question was, what happens to this? Yeah, how to deal with it? And the answer is, this is just one branch in a circuit. Now, maybe the geometry here bothers you a little bit, so you can pull it out and make it straight. But is nothing new. It's no different than any other circuit that you've solved. Finding the current I in this is no different than, for instance, finding the current I in this wire, or in this wire, or here, or So basically, all you have to do is make sure that you find a bunch of enough other currents that you can then, let's say, apply a KCL at one of those nodes to see what goes here. Okay. Remove this to avoid confusion for a moment. So this is the Thevenin equivalent. And again, remember that it's a property of linear circuits. Now, I want to ask you guys to do a quick exercise. Again, try something on your own. Take these IV characteristics. This is all that matters for a Thevenin equivalent. This entirely defines the Thevenin equivalent of the circuit, right? You have something in the box, and from the outside, it looks like this. We saw that you can construct this with, indeed, one voltage source in series with a resistor. Can you also try to construct this with a resistor and a current source? Can you try this on your own? So propose what I should put inside the box using a resistor and a current source so that from the outside it looks exactly like this, the same IV characteristics. Any suggestions? How about putting a current source in series with the resistor instead of a voltage source? So I just replace a voltage source, the voltage source with a current source. How about that? Any reason? Well, let's see what a current source in series with a resistor does. So now I want to talk about the Norton equivalent. So if I try to replace a circuit with something like this, what would the behavior be like from outside? So put a big question mark if this works. What would the behavior look like? So if I'm interested again in the same IV characteristics, so let's say I want to put a voltage source there and an ammeter, apply a voltage, measure a current, and then plot V versus I. What do I get? What's the IV characteristics of this circuit? Well, so let's say you take this to the lab, you build it, you put a voltage there. So you actually do the experiment. Let's do the experiment. So you put an ammeter there to measure the current, and you put a voltage source. So let's say this is 5 amps, and this is 2 ohms. Let's say I apply 10 volts here. This voltage source here, I apply 10 volts. What current does my ammeter measure? 5 amps, right? That I is just the current of that current source, 5 amps. What if I change, so 5 amps, let's say, for 10 volts. Now, this is not to scale, but doesn't matter. What if I change the voltage to 8 volts? What current will my ammeter measure? Same, 5 amps. And so on. If the voltage is minus 283, doesn't matter, same. So the IV characteristics here will look like this, a straight vertical line. The current is constant, okay? This is very special. This is not going to give you whatever slope you need for a general circuit, right? The Norton equivalent, like the Thevenin equivalent, will be something that will represent any linear circuit, okay? So this doesn't work. So if that doesn't work, what would another guess be? Let's try parallel. So I put a resistor in parallel. To a current source. And let me for now call this IN and RN. And I put this in a box. And I ask for the IV characteristics. So again, I'm not going to draw the ammeter every time and the voltage source every time, right? That's implied. I'm asking for the dependence of this voltage V on the current I, as specified on the circuit. So can you guys work on this? So let's see. So again, I hope we can agree that based on the same intuition from the past about linear behavior, that this is going to be a straight line with some slope and cutting the axes at some point other than the origin. And so I need 2 points to get that line. And again, I'll look for the 2 simple points, the crossings with the 2 axes. Okay. So for instance, if I had 0 current, in other words, if I actually left it open and just applied, connected a voltmeter there to measure the voltage, when the circuit is open, okay, what voltage would I measure? So what would V be if I was 0? So if I is 0, I have a circuit in which there is this current source, IN, going that way, right? I have a node up here. KCL will dictate that if I is 0, that entire IN should go this way, right? Right? So if V is 0, sorry, what did we say? No, if I is 0, then the voltage will simply be IN times RN. Oh, capital N. So that's one point on the line. Now what if V is 0? So if I'm interested in the crossing with the horizontal axis, so if V is 0, which means I have connected those 2 points with a wire, what will the current be that goes through that wire? So if I have this, what is the current I? It's just IN, because that wire has short-circuited the resistor Rn. So the voltage drop across Rn is 0, which means there is 0 current going through Rn because of Ohm's law. And so if you look at the KCL up there, it says that the entire IN should now go through this external wire. So then your short circuit current is simply IN. And that's that. So in this case, this is your VOC, and this is your ISC. So then the Norton equivalent is very similar. So for the same circuit that you had a Thevenin equivalent, so with the same conditions on linearity, you can also define a Norton equivalent. So similar to the Thevenin theorem and equivalent, and I don't want to write the whole description here, but if we have a circuit comprising resistors, linear resistors, ohmic resistors, independent sources and dependent sources defined by linear relationships, if we look between any 2 points, any again with the caveats we discussed, any 2 points in the circuit from the outside, the behavior of the circuit between those 2 points can be represented by a current source in series with a resistor. And maybe here I should have emphasized by an independent voltage source, an independent current source. So let me add that. An independent voltage source. And so we say the circuit with the same conditions as the Thevenin theorem can be represented by an independent current source in parallel with a resistor. Now, if you wanted to again come up with a guideline for finding the Thevenin equivalent, the Norton equivalent, well, same as before. Calculate or measure the open circuit voltage and calculate or measure the short circuit current. you see that your VOC in this case corresponds to Rn times In. And the short circuit current simply corresponds to In. So then from this you have In simply as your short circuit current, and Rn is simply the open circuit voltage divided by In, which you already have. Okay, so very similar to finding the Thevenin equivalent. The way to do it exactly the same as before, like the example we saw. When you are trying to calculate the open circuit voltage, you're just really calculating the voltage between the 2 points of interest. And remember, again, it depends on which points of the circuit you're interested in. And you solve the circuit and find that. In the next step, you actually have to add a wire between those 2 points, which means now a new circuit. And now you have to solve this new circuit to calculate the current going through that wire that you have added. And that's your short circuit current. And so that would directly give you your I Norton. And then dividing that open circuit voltage by the short circuit current would give you the R Norton. So what we did here is directly an example of that too. Okay. Now, having done these two things, and so we just talked about how for the same circuit you can have a Norton equivalent and a Thevenin equivalent. Well, if those two things are equivalent to the circuit between points A and B looked at from the outside, well, those two things should be equivalent to each other, right? So in fact, the Norton equivalent and the Thevenin equivalent are very closely related, and they can be very easily converted from one to the other. And this is how they are connected. If you look at the IV characteristics, you have this line, and same here. In the Thevenin picture, the point of zero current on the voltage axis is called the Thevenin voltage. In the case of the Norton equivalent, that point is called the product of the the Norton resistance and the Norton current. The point on the horizontal axis in the Thevenin picture is the division of the Thevenin voltage and resistance. In the Norton picture, it's just called I Norton. Okay. So it's really just a change of names if you think about it from an abstract point of view, right? And if, again, sitting from the outside, remember the whole notion of equivalent circuits means that sitting from the outside looking at those 2 points, you have no way to tell if inside there is a resistor in parallel with an with a current source, a resistor in series with a voltage source, or a big circuit with many resistors and dependent sources and independent sources, assuming everything is linear, right? So this is equivalence, and it's a very powerful concept. And here's an immediate thing. You can very quickly and easily switch between a Thevenin and a Norton representation. So this brings me to the notion of source transformation. That means switching between or transforming a Thevenin circuit to a Norton circuit and vice versa. I shouldn't say maybe switching, because this might create a confusion with switch. Switch is changing, let's say, changing between a Thevenin and a Norton circuit. And this is all you need to recall, that V Thevenin is equal to RNIN. So VTH is RNIN. And VTH by RTH is IN. Which really means RTH and RN are the same thing, right? So RN is VTH by IN, RTH is also VTH by IN. So switching from a Thevenin to a Norton representation is very easy. The resistor stays the same. If you had a current source, IN, all you have to do is to multiply it by that resistance, and you get the Thevenin representation, the Thevenin voltage. If you had the Thevenin voltage, you divide it by that resistance, you get the Norton current. The thing that will very often lead to mistake is directions. So pay very close attention to the directions. Maybe I'll draw them next to each other. So the way we have defined things. So this was my Thevenin circuit. So pay very close attention to the polarities. And this is my Norton circuit. The way I've defined things, and I stayed consistent throughout with my directions. Sorry. This is the two things that are equivalent as looked at from the outside. Okay? As long as that RTH and RN are the same thing, and VTH is the product of that resistance times IN, those two things are equivalent. They both have the same open circuit voltage, the same short circuit current, and entirely the same IB characteristics. All right, so I think that's it for today. We'll leave it at that. Next time we'll do some examples of source transformation, and then look at a special case of Thevenin and Norton equivalent, which is just equivalent resistance when your voltage is 0 or the current is 0. Okay, so thank you.